This talk is kind of complementing the last one. So he's made it clear that autonomy is becoming more and more important. We have large numbers of robots that are interacting in complex environments, and we need one thing that we need is to have a way to verify that these systems really do what we want them to do. So some way of verifying mission success. And some of the challenges here are that these, large, complex systems, lots of moving parts, lots of, autonomy, complex stochastic environments. So how we do this? Their systems are too big for formal verification methods. And so one technique that we've been approaching is statistical model checking. And so in the statistical model checking world, we have sort of a model, which could be your system of interacting UAVs or robots that have some random inputs, where the initial starting positions are, where the enemies are, what's going on in the environment, the wind. They're cooperating to do some mission. The other input to statistical model checking is a predicate, just a statement, maybe a specification of what mission success means. We apply a Monte Carlo simulation, possibly using importance sampling or adaptive sampling to reduce the simulation time, and get a sort of in the statistical model checking world, we say M models phi to mean that property in the system, basically the probability system of mission success to some level of accuracy. Relative error, for example, is one measure of accuracy. So now that's great, if we have a probability of success, but is that really enough? And so one of the big questions we're looking here is to go beyond just saying what's the probability of mission success. We want to go say why is that the probability of mission success? What factors affect it? So if SMC comes out and says you have an 85% chance of success, you immediately know how do I make it better? What factors are influencing that 85%? How can I improve that? All right, so I'd like to start with sort of a motivating example, a very simple example of a pursuer-evader game. So here we have sort of two drones. One is the evader, one's the pursuer. We have some safe zones in the corner. The evader is going to try to reach a safe zone before the pursuer catches it. If the pursuer catches it, then we consider that a failure. If the evader reaches a safe zone, we consider that a success. Okay. So now if we do that over and over again, and we simulate the model over and over again with lots of trials, using the statistical model checking we talked about, we can get an estimated probability of success. But now looking at the input attribution. What we call attribution is looking at the why did I get that result. And you can think of this as sort of analogous to the counterexample in model checking. If you're familiar with traditional model checking, you're testing a property, and when that property doesn't hold in the system, the model checker will give you a counterexample of why it doesn't hold. So this is kind of like the counterexample in model checking. Typically expressed in terms of what are the random inputs to the system. So in this system, we pick sort of the initial coordinates of the pursuer and the evader. So what would be the primary factors implementing success in this case? And so just looking at it as a human, we can sort of hypothesize, probably the distance between the initial distance is the primary factor. Expressed in like a Euclidean distance equation like that. But now, can we synthesize that automatically? I mean, we as humans can see that, but can we have a system that just looks at the trial data and synthesizes that expression? All right, so drilling down a little bit more, on input attribution, you can imagine that sort of all your samples have occur in some input space where sort of these axes represent different attributes, different random attributes like initial position, wind position, etc. And what we really want to do is we want to use techniques to sort of automatically figure out what the boundary is between those, and then give that boundary to the user in sort of a human-readable, understandable form. And so we've looked at sort of 4 attributes that we want that attribution to look at. It has to be something that describes actual relationships in the system. It has to be understandable to human. You want it to give you new insights about what's going on, and it has to be resilient to randomness in the system. So the approach we've taken is to use machine learning techniques, and specifically we've chosen to call logistic regression. And I'm not going to go into details on what that is, but the basic idea is to take a set of predictors, such as the input, calculate significance of those predictors, and look for sets of predictors that give us an interesting description of why you get a particular failure probability. All right, so as I said, I'm not going to go into details. Basically, it looks something like this. You have your inputs X, your random variables X. The logistic regression analysis will give you a set of coefficients. You see beta in that equation. And basically, this model will give you a prediction of the probability that a particular input vector will result in a failure or success, whichever way you define it. So here's an example of an output you might get for a case of 4 random variables. Basically, you get the beta 0 term, the constant term. For the purposes of input attribution, we don't care too much about that. You have your set of random variables, the beta coefficient, which is the primary output of the logistic regression analysis. And I'm not going to go into details about the interpretation. I'm just going to say the positive values mean that as a particular variable, such as wind speed, position, et cetera, increases, that means the probability of the predicate, the mission success or whatever, being true increases. If it's negative, then as the variable increases, the probability of success decreases. Other things you get out of that are there's a standard error, and then from that you can calculate a p-value, which is a measure of statistical significance. You can think of the p-value as being the probability that a coefficient value of 0, meaning that variable or predictor has no influence, could be true. And so if typically we'll pick like a 5.05 threshold, and so if that p-value is greater than 0.05, we consider that not statistically significant. So in this example here, that fourth predictor was not significant. Okay, that's great for linear cases, but lots of examples, the relationships between the variables and the predicate may not be linear, and so we need to figure out how to do that for nonlinear cases. And so we've focused on quadratic polynomial cases. So in this case, in addition to sort of the linear predictors, the variables by themselves, we also include polynomial terms, such as x squared, y squared, xy. Of course, we can look at higher order polynomials or other functions besides polynomial functions as well. And we apply factoring. The factoring is speaks to the goal of trying to make this more human readable. But since these coefficients are sort of random approximations, often they won't factor cleanly, so we have to have sort of an approximate factoring method. So here's an example. Maybe we get a factoring that looks like this. So now we've have an x squared, xy, y squared as variables as predictors. We get coefficients for it. Now we try a complete the squares to create a candidate factoring, and if we re-expand that, we get sort of the expanded coefficients, and then we compare those expanded coefficients to the values on the tables, like the minus 0.204 you see from the table, and the plus 1.03 on the y squared term. You see that's very close to the 1.02 as the predicted value, and since that is sort of within the standard error or a small number of standard errors, then we accept that approximate factoring. All right, so all this has been implemented in a system that we call Demeter that James talked about. Demeter is implemented on a set of blade servers. We have currently have 6 blade servers, but it's sort of extendable to however you want. Has sort of a web-based interface, so you just use your regular browser to connect to it. And we use some software called Docker to provide isolation for the simulation, so we can do hundreds of simulations in parallel at once to get approximations quickly and data quickly. All this is stored in a database, and the input attribution, which I've been talking about, is implemented in a system called R. It's a statistical package that's very popular. Okay, I'd like to talk about a couple examples. The first one is, which I call a target threat example. So if you imagine you have a set of famous physicists that are hanging out on the beach, you have a paparazzi who wants to take pictures of these famous physicists, but the physicists have bodyguards with shotguns. The paparazzi has decided, he wants to get low to the ground with physicists to get good photos, but he wants to avoid the bodyguards with the shotguns, so the drone is going to have to fly higher when he goes over the bodyguards. And we have another group. I'm not sure if he's talking to James. Gabe Moreno has developed an adaptive algorithm that uses sensor inputs, predicting ahead of time what kinds of targets and threats are going to be, and controls whether the drone should go up or down. And so we want to know how well does this work. Okay, so some of the inputs of here are the number of threats, the number of targets, the range of the down pointing camera, the accuracy of the forward sensors, the range of the threat, the shotgun that the bodyguards have. And now in this case, our predicate is that we want the drone to be able to photograph at least 50% of the physicists while avoiding getting shot down by the bodyguards. All right, so here's some of the results. Sort of in that upper box, you see sort of the basic SMC results. We did 22,560 trials in 10 hours and 6 minutes. And this, again, is using physical simulation with VREP, just like James talked about. Broken down the probabilities into, when I say sat here, that means satisfied, that the predicate is satisfied. So if I say PSAT mission, the mission success is satisfied. And I've also broken that down into survival, the probability that it survived to the end, and PSAT detect would be the probability that you detected at least 50%. So broke that overall mission success down into the sort of the sub-predicates. Now, if you look at the bottom table, that's the input attribution results. So under the name are the different input parameters, looking at, and I'm going to point some observations out. I'm going to speed up a little bit since I'm running low on time here. So one thing we notice is that false positives on threats reduce the probability of detecting targets. So sort of a crossover effect here. You can see that from that value. So one explanation for that is that because when you have those false positives on threats, you're reacting to threats that aren't there. The drone is going up, and so you do a poor job of detecting your targets. Another thing you can see from here is that increasing the number of targets reduces the probability of survival. So you have more physicists, mean you're more likely to get shot down. And a reason for that is that when there are more physicists, there's more bait, basically, so the drone stays down lower, and he's more likely to get hit by one of the bodyguards. Another interesting thing we noticed, we're still not quite sure the reason for that, is we found that there wasn't a statistically significant result on the false negatives. So false negatives on both the threat and the target were not showing up as statistically significant, and we even verified that by going through again and doing drill down experiments to show that's the case. Okay, sort of the last example I'd like to go back to that pursuer-evader one, and remember that our initial hypothesis in the pursuer-evader case was that the distance was the deciding factor. And so when we did the results, so you can see the results and the input attribution, and when we factor it, we get that expression there, and you can see that that expression is basically very close to Euclidean distance. So that was synthesized entirely using the input attribution technique. So in summary, input attribution addresses the Y of SMC, showing sort of what variables important, what relationships between the input variables important. We implemented in Demeter and some future work. Of course, we can look at other things besides logistic regression or other types of nonlinear cases.